Good morning, everybody. Thank you. I'm George, if we haven't met yet. I'm from the New York office. This is going to be an introduction to machine learning. This workshop, we have an hour scheduled. It's going to be in kind of 2 acts. So Act 1 is going to be some information. I'm going to present some slides, talk through what machine learning is and what it can do from a very high-level conceptual perspective. And then Act 2, I'm going to do some live coding to build a very simple machine learning system to solve a problem that is too simple that we shouldn't be solving with machine learning, but it's just there as an example. First part's going to be about 20 minutes. Second part's going to be about 40 minutes. We're all friends. Feel free to interrupt me and ask questions and all that kind of stuff. So, first things first. What is this machine learning thing? It's probably best to focus on the word learning and think about how you learn things, because from that analogy we can figure out how machines learn things. How do you know the things that you know? How did they get from being like concepts out in the world to being things in your brain? So there's 2 ways that this typically happens. One is rote learning, things that you explicitly memorize. So for example, I know that the sine of an angle is the ratio of the opposite and the hypotenuse, and I know this because in high school math class I was taught this mnemonic. Silly old Harry caught a herring trawling off Afghanistan. Silly old Harry, SOH, sine is opposite over hypotenuse. Every time I need to use this branch of mathematics, I can recite this rhyme to myself. I've explicitly memorized this information. Every time I use this branch of mathematics, I'm slightly angry because Afghanistan is a landlocked country and there are no herring and no trawling and I don't know what's going on. But it's a form of learning, right? I've memorized this thing, however silly it is, and it allows me to use this branch of mathematics. But Afghanistan is a large landlocked country, which brings us on to the next type of learning. Think of that phrase, a large landlocked country. If I'd instead said a landlocked large country, native English speakers among you would probably have gone, oh, that sounds wrong. That doesn't totally make sense. You probably meant to say a large landlocked country, not a landlocked large country. Can anybody tell me why? There's always one.
All I know is that there's some kind of natural ordering for adjectives that we all kind of ascribe to.
Right, some kind of natural ordering to adjectives that we all kind of ascribe to. So as a native speaker, you've grown up your entire life hearing people speak in this way. You've been exposed to so many examples that you've just kind of internalized this set of rules. But I would doubt that any of us here could articulate what the rules are for adjective ordering. I'm not even sure what type of adjective landlocked is. I don't know, like, I know large is a size, but landlocked? But somehow I know it comes after sizes, whatever it is. This type of learning from exposure to examples, from repeated exposure, is different from the memorization. But you can kind of work backwards and figure out what the rules are, but you didn't learn the rule and then start applying it. You were already applying the rule before you even were aware that there was a rule. So what's this got to do with machine learning? Well, most of the programming we do is more like the first kind of learning, that explicit rote learning. We write down a series of very explicit instructions and the computer carries them out. We go from rules to a working system. Machine learning systems are more like the second kind of learning, more like adjective order, where we go from a whole bunch of examples, and then from that, we get a system that can produce the right outputs through exposure to the examples, even if we don't fully know what the rules are. Wikipedia puts it like this: machine learning uses statistical techniques to give computers the ability to progressively improve performance on a specific task without being explicitly programmed. So we're not explicitly defining the rules. We're just exposing a system to enough data that the rules are inferred. That's pretty powerful. It lets us build systems where we don't know what the rules are. Like, we could build an adjective ordering system without ever having to go and read a linguistics textbook and understand what the adjective order is. We could build a face detection system without ever having to sit down and think through the steps of what makes this image a face and this image not a face. It also makes it a little dangerous. it's worth thinking about the fact that the rules that machine learning systems infer, they infer from the examples that we show them. So make sure you're showing them the right examples if they're going to infer the right rules, right? If you're building a face detection system and you only show it examples of white faces, you've not got a face detection system, you've got a white face detection system, and that's not what you were trying to build. It's really much easier when you're not explicitly writing out the rules to build a thing that you didn't intend to build with pretty terrible results in some cases. So we don't know what the rules are, they're inferred from the data, that's very powerful, it's also quite dangerous and something that you need to think carefully about. Any questions so far? Is everybody with me? Everybody happy? Doing all right, thanks Adam. Any other questions? Okay. So that's kind of roughly how it works from a high level. What can this do for us? What kinds of systems can we build in this way? I'm going to talk about two broad families of machine learning now. There are others, but these are kind of the major ones, and we only have an hour. The first one I'd like to talk about is supervised learning. Supervised learning is where you start with what we call a labeled data set. That's examples of the input that you expect to see and examples of the output that you want. So here is a labeled data set. The inputs that we have are an alphabetized list of adjectives. The output that we want is those adjectives in the order that a native English speaker would say them naturally in a sentence. It's somewhat difficult to build this kind of data set because if there was an easy way to go from the input to the desired output, we wouldn't need to build a system to go from the input to the desired output in the first place. So usually this involves a lot of manual effort. There's a lot of human labor involved in getting this set of examples together because we have to write the labels by hand usually, or crowdsource them, or do something to get them from humans rather than from machines. And the goal of a supervised learning system is to be able to generalize to examples it hasn't seen before. So having been exposed to landlocked, enlarged, and red and small, and thousands of other examples, if we show the system big and green, which it hasn't seen before, can it figure out what the right order of the words should be? So supervised learning is used for various things. One of the most important is classification. Classification is where we have things of different types, and we as humans can tell you what types they are, but we don't necessarily know the rules that define one type from the other. So here I have some points on a scatter plot. Some of them are red, some of them are blue. If we wanted to build a system to distinguish the red ones from the blue ones, we could use a classifier. And what our machine learning algorithm would do here is it would draw pretty much a random boundary, and it would say, how did this do? Did it separate the reds and the blues? And it probably wouldn't because it was a completely random boundary. So it would move the boundary slightly. It would figure out what direction it needed to move it in to get better results, and it would move it very slightly. And then it would ask the same question. Is this separating the reds and the blues? Well, slightly better than before, but not really. And it would keep moving it very slightly, very slightly, very slightly, until eventually you'd end up with a boundary that made sense. So this boundary was actually found by a machine learning algorithm. Like these diagrams aren't just pretty slides, and I'll share the code that generated them afterwards. But this is a boundary that sort of sensibly separates the reds and the blues. If a human had drawn this line, it probably would be in about the same place. It's interesting to note that this boundary isn't perfect. Like there are some reds and some blues that are on the wrong side of the line. We could have drawn a really complicated squiggly boundary that kind of caught all of the examples and got every single case. But remember I said we're looking for something that can generalize to new examples that it hasn't seen before. We want to be able to like throw a dart at this and say, okay, wherever that landed, should that be red or blue? If we drew a really complex squiggly boundary that caught all of the subtleties in our training data, that matches the training data really well, but it probably doesn't generalize to the overall problem we're trying to solve. So there's a balance to be struck between how well we're modeling the training data and how well we're modeling the entire problem domain that we're trying to look at. Everyone on board? Mm-hmm. You're all very quiet.
How is this different than a hill climbing algorithm?
So Joel asked, how is this different from a hill climbing algorithm? So actually, the algorithm that would do this uses gradient descent normally, which is very, very similar to hill climbing. So hill climbing is saying, how can I maximize some function, like how can I climb to the highest point? This is usually saying, how can I minimize some error function? So how can I like descend to the lowest point? But otherwise it's very similar with all the same problems you get with hill climbing, like local minima and maxima and those kind of things.
So machine learning is adding something on top of this descent thing?
So is machine learning adding something on top of this descent thing? Machine learning is using the gradient descent. So I guess a hill climbing algorithm I would probably also class as machine learning in that it is iteratively, like based on some data, it's iteratively going to find an answer for us. So it starts off doing quite poorly and then it learns as it goes what a better answer is iteratively over time. Does that make sense?
I thought of hill climbing as a machine learning, but it makes sense the way you presented it.
Yeah, it's, I guess, it may not always be. So hill climbing and gradient descent, they're both optimizations, and you use optimization in machine learning to learn what the answer should be from some data. You can also use optimization for other things which aren't machine learning, probably. Like if you just have a function that isn't based on some existing data, for example, then that's maybe not machine learning. But very similar tools, like optimization is a central part of a lot of machine learning algorithms.
You mentioned gradient descent. Are you more specifically focused on neural network-based machine learning?
So I mentioned gradient descent. Am I focusing on neural network-based learning? I am going to build a neural network in the live coding section, but gradient descent's used for other models too, for linear regression, for logistic regression. This boundary was drawn by a logistic regression algorithm, which isn't using a neural network, but is using gradient descent. And usually there's a thing like gradient descent. Like there's some kind of optimization function happening for many, many types of machine learning algorithms. So gradient descent's one example, but there are others.
I have a question. I'm sort of confused if this is like a one-time thing that happens, or like when you do gradient descent, you like regress to zero plus or minus some error boundary, and is machine learning that continuously happening, or does that happen one time and then we match it against the results of like the optimized gradient descent line?
Yeah. So is this kind of gradient descent optimization process a one-time thing, or is it something that's continually happening? I'm going to give the classic thoughtbot answer. It depends. But usually it's a one-time thing in that usually you start from a data set, you train it like I've found this boundary now, so now I've done this process of optimization of finding the right boundary one time. I can now use this boundary over and over and over again, but usually after you've used it for a while, things have changed enough that you should probably retrain. It depends on the domain, I guess. Like if you're building a face detection system, then once you can detect faces well, you're probably fine. Like the human face is not going to change fast enough that you need to worry about retraining. But if you're, say, training a model on some data about how visitors behave on your website, you probably want to retrain that model regularly. And there are types of learning, like there's reinforcement learning, for example, where you keep feeding in new examples as you go. So let's talk about a specific classifier just to make sure this is like rooted in solving problems for people. So this is a page from the Apollo 13 transcript from NASA. And at the end of last year, a few of us in the New York studio, we built a OCR program for this data. So we wrote some like normal traditional computer vision software with no machine learning. Adam?
What's OCR?
Oh, OCR is optical character recognition. So it's turning images into text. So we wrote some code to extract the characters from this, and then we labeled a whole bunch of them by hand. Here's an example of the web application we used to label them. And then we trained a classifier, and the classifier was able to say, is this an A, is this a B, is this a C, is it a 0, all those kinds of distinctions. So this may seem kind of different to like just drawing a line in a plot, but it's actually, like the algorithms and the mathematics behind it is very similar in that while this is a two-dimensional space where you only have like X and Y properties, when you're classifying an image, you have many, many, many properties representing all the different pixels within the image. It's a higher dimensional space, but it's still the same process that you go through. There's still a boundary being drawn. It's just the boundary is a mind-blowing hyperplane that's very difficult to think about without getting a headache. One thing I didn't mention here actually is that with some of the reds and blues being on the wrong side, like classifiers aren't entirely precise. Usually the output you get from them is a probability, not a hard answer. So the examples you're showing to it are hard answers like this is an A or this is a B, and then the result you're getting out the other end is like, I'm 90% sure this is an A, but like 10% it could be a B. I'm going to move on to unsupervised learning, unless there are any more questions in this area. All right, unsupervised learning. So this is learning based on just the data set itself. You don't have to label the examples with this is the answer I'm expecting to get out at the end. This makes this kind of applicable to different kinds of situations, but also somewhat easier to get the data together for because you just need some data. You don't also need human judgment in the process. Unsupervised learning, generally you make a statement about the data, and then the algorithm learns how to apply that statement to the data that you have in front of you. So a common example of this is clustering. So again, we have some random points here, and I'm going to make the statement that there are 3 clusters within this data. There are 3 groups of points that are somehow associated with each other within this. And very similar to the supervised learning, we start with just 3 random points, and then the algorithm looks at how well they did at grouping the data into 3 clusters, and progressively gets better and better and better until it arrives at 3 center points that kind of make sense. And we can assign each point to the cluster that it's closest to. That makes sense?
When you say starting with 3 random points, where are those points coming from? Are you telling it? Is it just automatically generating coordinates, points? Like?
Yeah, so when I say it starts with 3 random points, where do they come from? So the number 3, the fact that there are 3 points, comes from me. Like I decide I want this many clusters, but then the algorithm will just use random number generation to pick the 3 points. So it's just using whatever system random number generator is available. Yeah.
And like in the previous slide, you showed like a line, like it found the separation between the 2 sides. Why is this not finding like lines that separate it? Why is it finding points? Because you also told it that.
So the question was why in the previous example there was a line. In this example there are points. Why is this finding points instead of lines? I guess I could have visualized this with lines that say, you know, this is the boundary between points that belong to this cluster and points that belong to this cluster. But it's more the way that those separate algorithms work. So logistic regression is explicitly finding a boundary line. That's what the output of that algorithm is, a boundary line. The output of this algorithm is points that these are the centers of the clusters. And then you just use the distance from a center to determine which cluster something belongs to.
And how do you tell it like what a cluster is?
So how do you tell it what a cluster is? So an unsupervised learning algorithm always has certain assumptions and biases kind of baked into it. So the algorithm I'm using here is called k-means clustering, and the assumption it makes is that things being close together makes them a cluster. So this is entirely based on distance. There are other algorithms that have other ways of defining what a cluster is, but in this case it's all about just proximity, it's all about distance. To give a concrete example of clustering, here is a data set, or a photo of Lindsay, depending on how you prefer to think about it. Each pixel in this photo has, as we heard in Stephen's lightning talk yesterday, each pixel has a color, and each color can be thought of as a red component, a green component, and a blue component. So we can plot the red, green, and blue in 3D space, and we get this distribution of points. So the origin of this would be black pixels, and then the extreme opposite corner would be white pixels. if we run a clustering algorithm over this distribution of colors, like I could run the k-means clustering algorithm with 6 as the number of clusters I want. I get 6 points which map to colors. So these are the 6 colors that are predominantly present in this image based on this idea of clustering on distance, which actually is the same. It's the same measure of similarity of colors that Stephen was using in his Guess the Hex Code game. So why is this useful? Well, there's a couple of things. One is aesthetic purposes. Like if you want to pick a color to go with an image for a background or whatever, you can automatically do that using this kind of clustering. Another thing this can be useful for is recognition. I used this same algorithm once in a program that was trying to automatically play a card game. So given a photo of the cards, it could figure out what a card was based on the primary colors of that card, which was quite useful for playing that particular game. You can also use it for compression. So I can replace every pixel in this photo with one of those 6 colors, and now I have the best possible representation that only uses 6 colors. If you remember the early days of the web, you probably saw a lot of images that looked like this, because bandwidth was limited and compression was required, and these kind of clustering algorithms were being used to do that compression.
All of this can happen without machine learning. So this kind of clustering and finding the colors.
So
imagine they weren't using machine learning in the early days of the web to compress images.
So Joel's question was, can all this kind of clustering happen without machine learning? I imagine in the early days of the web they weren't using this. I think it was just less trendy to call it machine learning back then. A lot of machine learning is really just applied statistics, which sounds way less sexy, but is stuff that has generally been known about for a really long time. Like the mathematics behind this is usually stuff that's been well known for a long time. And the reason machine learning is exploding right now is that computers have got fast enough to apply this to significantly larger data sets or to apply significantly more complex statistical models. So we suddenly have a cool name for this whole field. But this kind of clustering algorithm is a real example of machine learning and a real thing that has been used for a long time that is machine learning. This is the end of Act 1, so if anyone has any more questions before I make a fool of myself by typing Python in front of you all.
What's the difference between machine learning and artificial intelligence?
That's a good question. So what is the difference between machine learning and artificial intelligence? So artificial intelligence is a larger family of things. Like machine learning is a subset of artificial intelligence. So machine learning is specifically using this example-driven statistical modeling to build systems that can produce results without us fully understanding what's happening in the middle. There are other ways of doing that, which are other forms of artificial intelligence, which I don't know enough about to speak to intelligently, but they exist. Adam?
So my question is about this specific example. How are the colors determined? Is that by measuring, is that using like a color distance function like we saw yesterday?
So in this example, how are the colors determined? Is that using a color distance function? So do you mean the colors of the 6 colors?
Yeah, like those 6 colors aren't necessarily just like an actual pixel from the picture, right?
Yeah, they're not a pixel from the picture. What we did was started with 6 random points anywhere in the RGB color space, but it's an RGB color space, so every single point represents a color, like some color. And then we applied that same clustering algorithm of saying like, okay, how well do the points that we have in the image group around these 6 random points that we've picked? And we move the points slowly over many hundreds of iterations to the right places where they really do fit well with the data that we have in the image. And then because those points exist in a RGB color space, it's just the RGB values for those points that then determine the colors. Does that make sense?
So what does fit well mean in that case?
Moving until they fit well, what does that mean?
So the question was, what does moving till they fit well mean? So the way that this specific k-means clustering algorithm works is you pick a random point and you say, okay, which are the points we have in our image which are nearest to this random point that we chose? And then you say, okay, what's the average of the random points that we chose? Oh, well, it's kind of over here, so I'll move my center to over here and then rerun the algorithm. So what are the points nearest to there? Okay, what's the average of those? Oh, it's kind of over here, and through that process, it kind of slowly drifts to the right place.
But I suppose, just to clarify my question, I think my question is it choosing a random point in RGB space or in the XY coordinate space of the image?
Oh, I see. Is the random point chosen in the image or in the RGB color space? It's in the RGB color space, yeah. As far as the algorithm is concerned, the image does not exist. The only thing that exists is this distribution of points in RGB color space.
Are there multiple solutions? Like, can it get stuck in minimums and minimums?
Are there multiple solutions? Yes, and actually this particular algorithm, k-means clustering, can perform terribly if it picks the wrong starting points. Usually the solution to that is just to run it a whole bunch of times and pick the one that you feel best about. Or pick the one where the clusters seem most coherent. So the one where like the average distance from the center of the cluster to the points within the cluster is the smallest. So if you end up with these really kind of big, long, spread out clusters or just weird shapes, then probably not great compared to like really dense clusters.
Is it deterministic?
Is it deterministic? With the same random start points, yes. With different random start points, no. There is randomness involved in most of these algorithms, and the results can be somewhat vague. Like, this is all based on statistical modeling, which means all of it is a best guess. Even with the best models, they have a high probability of success, but they don't guarantee a perfect outcome. We're going to see that in the live coding demo.
This reminds me of Voronoi diagrams. Are the algorithms typically used to sort of figure out where to put the Voronoi centers and to cut out the space? Is that essentially what you're doing here? And would that be considered machine learning?
The question was, this reminds me of Voronoi diagrams, and is this how Voronoi diagrams are built? And my answer is, I don't know what Voronoi diagrams are, so I can't answer the question. I'm sorry.
Why wouldn't we do something like an initial Bayesian pass to find priors to do like a better estimation of what the starting points would be? Is the danger overfitting? Or like I don't. Why wouldn't we do some sort of like pre-analysis to get the best possible starting points to optimize the algorithm?
So why wouldn't we do some kind of pre-pass, some kind of Bayesian filter, for example, to figure out what the likely good starting points would be? That's a good question. That may well work. I don't know. Sorry.
So this reminds me a lot of like a JPEG compression algorithm or something similar. How does it perform compared to like a compression algorithm that does like a running average or a moving average?
Yep. So how does this kind of compression compare to a moving average like JPEG compression? I think the main difference is that the images you get out of this style of compression look like this. So the compression artifacts you get here are the fact that it's all in these kind of big blocks of solid color, whereas JPEG compression is much more subtle. I don't know how the image sizes would compare. I think we're going to move on to the live coding. So, Act 2. Who is familiar with the game fizzbuzz? Okay, I'm not seeing every hand, so fizzbuzz is a children's counting game, which has been co-opted as a terrible, terrible interview question by software development companies everywhere for some reason. The way fizzbuzz works is that each player in turn says a number, but if the number is divisible by 3, you don't say the number, instead you say the word fizz, and if the number is divisible by 5, you don't say the number, instead you say the word buzz, and if the number is divisible by both 3 and 5, you say fizzbuzz. So, for example, 1, 2, fizz, 4, buzz. Right, so we're going to build a machine learning system that can play fizzbuzz. This is going to go great. So the first thing I'm going to do is implement fizzbuzz in the normal way, the way that you really should implement fizzbuzz. So we start by saying that fizz is, if we take the number and we take the remainder from integer division by 3, if that's equal to 0, it's a fizz. And with buzz, it's the same thing, but it's integer division by 5. If the remainder from that is 0, then it's a buzz. So if fizz and buzz, we want to return fizzbuzz. Elif just a fizz, we want to return fizz. Elif just a buzz, we want to return buzz. And then the final case is that we return a string representation of the number itself. So let's look at some output, see if we got that right. For n in range from 1 up to 15, ranges in Python are exclusive, so 116 actually gives us 1 to 15 inclusive. So for numbers in that range, we want to print the fizzbuzz for that number. So 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, fizzbuzz.
You're hired.
6-year-long interview process. Yeah, so here's our regular implementation. This can produce perfect tensors every time. We really ought to stop here. We really shouldn't build a machine learning system. But if we were going to do this with machine learning, the first thing we'd need is some examples of what the output from fizzbuzz is. So I'm going to start with the Python random package and say I want a random sample from the range from 1 to, let's say 1 million. And I want that sample to be 100,000 examples. So we'll call this numbers, and we'll look at the output of numbers. So that's 100,000 numbers in the range of 1 to 1 million. This programming environment I'm using, by the way, is called Jupyter Notebook. This is very, very popular in the machine learning, data science kind of areas because it's a really good environment for experiments. You can rerun individual blocks of code multiple times. It can do inline visualizations with graphs and charts and things. All of the graphs and charts and weirdly colored images of Lindsay and animations and stuff, I generated all those in a Jupyter Notebook before the presentation. So I have some numbers here, but what I really want is examples. So what I want is both the number, which is the input we want our system to accept, and the fizzbuzz, the answer we want our system to produce. So I can do that by saying I want n and fizzbuzz of n for n in my numbers. So these are some examples I can use, and I'll just assign that to a variable. Getting better. We now have both the number and the fizzbuzz. That's the input and the output, but this is still a list of tuples, pretty primitive Python data structures, and instead we'd like to use pandas, which is the first of the machine learning tools in the Python ecosystem that I'd like to introduce you to. So we're going to import pandas alias to PD, which is a convention that people generally follow. What pandas is really good at is dealing with tabular data. So I'm going to create an instance of a pandas data frame object that contains my examples. Don't worry too much about those warnings. They'll be fixed in a future version of pandas. So here are our examples now presented as a pandas data frame. The first advantage of using pandas that we're noticing here is that Jupyter Notebook knows how to output this as really pretty HTML, but there'll be lots of other things we use pandas for as we go along the way. I also want to name the columns here. So the columns are going to be called n and fizzbuzz. And we'll assign this to a variable called examples. So we're overwriting our examples variable, but with a pandas data frame, which is much more useful. And then one thing we can do with pandas here, we can call a head method to just see the first few. So there we go. That's the first 5 of our examples in a pandas data frame with nicely named columns. This is where most supervised machine learning problems would start, right? I have the examples now. I generated them because I already know the answer. I was cheating, you should ignore that part. But I now have a large set of examples in a pandas data frame. So the next thing we do is called feature engineering. I've been talking about using these statistical models to like model the way that input should be mapped to output. Statistical models only really deal with numerical information. They don't deal well with other types of things. And I have other types of things here, like the word fizzbuzz is not a number. Really what this is a classification problem. For any given numerical input, I want to be able to classify it as either a fizz, a buzz, a fizzbuzz, or the number. Right, so I have 4 categories, but really I can get away with 2 of them. If I know if it's a fizz or a buzz, then I can kind of infer the rest from there. We'd probably have to, again, if we didn't know what the answer was here, we'd probably have to experiment with setting up all 4 categories and setting up just 2 categories and seeing if it did make sense, but I'm cheating slightly for the interest of time. So this fizzbuzz column is not as useful to me as separate fizz and buzz true and false columns would be. So I'm going to engineer new features in my data set based on the features I already have. This is where pandas is awesome. So I can say examples fizz is going to be derived from examples fizzbuzz. And we're going to use a string operation on this, which is the contains operation, and we want it to know if it contains fizz. So let's look at our examples head again. You can see we have this new fizz column, which is false, 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 true, false, true when fizz was in the fizzbuzz column. And we can do exactly the same thing with buzz. So now we have both fizz and buzz columns. So I've used feature engineering to take this one complex fizzbuzz column and turn it into 2 features that are more appropriate for a classifier model. These are called our target features because these are the output that we want to get to. Everyone with me so far? Cool, okay. Next, we want to look at our input features. Like, what are the features of the input that we can look at to figure out what the output should be? Now, I said that statistical models deal well with numbers. My input n is a number, so that might be fine. It turns out it isn't fine. I tried training models with just the number, it didn't work. So there's a common trick that you can use to represent numbers differently to see if maybe the classifier will find patterns that way, which is to represent the numbers as binary digits. So each binary digit is going to be a separate feature. So if we're going to represent these numbers as binary digits, then we need to be able to convert numbers into binary digits. So let's define a method called bits, which does just that. So it's going to take a number, and it's going to take the number of bits we want it to output. I'm just going to always use 32 here. And we want to return format the number as binary. And we're going to zfill, which is fill with zeros, up to the number of bits that we want. And just to see that we're doing this right, I want to print bits 1, 2, 3. So that looks like a 32-bit number, but I want each of these to be a separate column. Oh, sorry.
I just want to make sure when you say binary digits, you mean sequence of binary representing a decimal number.
Yes, so I mean a sequence of binary representing a decimal number. So this is the binary representation of 1, 2, 3, and I'm going to split this into separate binary digits, which still represent 1, 2, 3. But each digit is going to be considered a separate feature by our model. So let's do that. Let's convert these into separate things that our model can consider individually. So we want to take that binary string representation and actually return the integer value of each bit for each bit in the binary. And if we run that again, yeah, so we're seeing the same output, but now every binary digit is a separate field.
Is that because previously each number by itself was just one feature?
Is that because previously each number by itself was just one feature? Yes. Often a number just being a feature on its own works pretty well. In this case, I'm going to use a neural network model, mostly because I want to. If I was doing this as a real world problem, I would try out multiple different models and find one that gets the best results. Again, for the interest of time, I'm only going to build one thing. And I tried building a neural network that only considered the number as a feature. It didn't work very well. That's because this is a kind of recurrent pattern in the data, which neural networks don't really do well at spotting unless they're very deep, complex neural networks, which take a long time to train, and there's a lot more figuring out to do. So we're just going for this binary, each bit as a feature representation, because it allows us to use a simple classifier which we can build and train more quickly. Does that make sense? You notice I'm talking like there's a lot of trial and error. I'm saying if I was doing this for real, I would do more experimentation. I have done some experimentation in preparation for this. That's because there is some trial and error in this. Like, one of the things I said earlier was that we don't necessarily know what the rules are. We're trying to build models that perform well. So how do we know the model performs well? Well, we've got to build a few and find out. But returning to this specific model, let's take our bits function and apply it to our examples. So I want to say apply bits to n for each n in examples and the examples n column. So this should give me a list, and each list should contain another list, which is the binary digits of the number. Yep, that looks about right. So let's put this in a pandas data frame. See what that looks like. So that's a little easier to read, and we can give these columns names. So I'm going to say bit columns is, I want these to be named like B0, B1, but I don't want to write out all 32 of these, so let's just do a little bit of metaprogramming here. We'll just say that. Something like that to get our column names. How does that do? So now we have column names, and then we can assign this to bit data. And because bit data is a data frame, we can use our old head method to just look at the output. Okay, so we have 32 columns, each one containing one of the binary digits. The next thing we want to do is put this into our main examples data frame. Pandas, again, helps us a lot here. So there is a concat method which will concatenate two data frames. So we can take examples and bit data, and we want to concatenate them along axis 1. If we used axis 0, it would be adding rows rather than adding columns. And so we use axis 1 to concatenate by adding columns. There are our examples with the bit data concatenated. And I'm going to reassign the examples variable again to contain this. And we can just output the first 5 rows. How are we doing so far? Everyone feeling good? Okay, so what we've done now is we've finished our feature engineering stage. We have some features that we think we're likely to be able to train a model using. So the next step is to divide our data into 2 parts. I mentioned that supervised learning, our goal is to make something that can generalize to examples it hasn't seen before. The only way we can test that is by keeping some of our examples back that we haven't used in the training, so we can use those in evaluating our model. So to help with this, we're going to introduce another Python library which is very useful for machine learning, which is SKlearn. SKlearn stands for scikit-learn. Scikit is a Python library for scientific computing, and SKlearn is their machine learning library. So there's a ton of really useful stuff in here, including a model selection module, from which we can import a train test split function. This will do exactly what we've just discussed, with splitting up our train examples and our test examples, starting from our examples. And the test size is going to be 20% of the total. So a nice thing here is that our train examples is actually going to be a pandas data frame, and so is our test examples. The scientific computing and machine learning data science tools in Python work together really, really well. This is one example of that, where our data's in pandas and it can just stay in pandas, and SKlearn plays very nicely with that. So let's take a quick look at this data in a bit more detail. One thing I would like to do is look at the representation of fizzes and buzzes within my training examples. So I can use group by, and I can group by fizz and by buzz, and then I can look at the counts on this data. Oops, I didn't mean count there, I think I meant shape. And shape is a method. Size. Size is what I want. Goodness. Okay, so count, shape, size, all real things. Anyway, the size of this, we can see that for numbers that are neither fizz nor buzz, we've got about 43,000 of them. For ones that are just buzz, we've got about 10,000. For ones that are just fizz, we've got about 20,000. And for ones that are fizz and buzz, we've got about 5,000. So that's about what we'd expect. And that's going to be useful to know that we are training on data that represents all of our classes. It doesn't, just represent fizz buzzes or just represent numbers that are neither fizz nor buzz. Now, we generated this data, we know the rules, so that was unlikely to happen. But in a real world scenario, we would definitely want to check that we were training on a set of data that was kind of representative of the problem space that we had. So we're ready to actually go ahead and build a machine learning model. We're going to stick within SKlearn, and we're going to use a neural network. I'm going to import an MLP classifier, which is a classifier. So we know this is a classification tool. And MLP, that stands for multi-layer perceptron, which is the simplest kind of neural network. Don't worry too much about the details at this point, but it's sufficient to say that a neural network is a statistical model, and it's modeled on the structure of the human brain. So the idea is that there are lots of individual neurons which are connected to each other in a network, and each neuron will output something depending on what its input is, so signals kind of propagate through the network. So in our case, our input is going to be our bits, our 32-bit fields, and then the output is going to be two items, which are the fizz true-false and the buzz true-false. And actually, it won't output true-false, it will output a probability, and we can use a threshold to turn that into a true-false. So let's make an instance of that. So I mentioned it has this kind of network structure. We need to say what our hidden layers are going to be. So in this case, we're going to have 32 inputs and 2 outputs. So we'll put 32 hidden layers in between. I think that's actually hidden layer sizes. And then we want this to be verbose, so that we can see output about what's going on, and we want the maximum number of iterations it can go through in its training process to be 1,000. Oops. SKlearn, not SKlean. There we go. So we've created the classifier, but we haven't yet trained it. So far, all of the neurons in here, those 32 input neurons, 32 hidden neurons, and 2 output neurons, they all just have random initializations, random weights. Could be any value at all. So in order to conform them to our data, we need to call classifier.fit. Classifier.fit is going to take what the input should be and what the output should be. So that's going to be our train examples for the bit columns. We want the values from those. And then our train examples for the fizz and buzz columns, and we want the values from those. This is going to take about a minute, so good point for questions.
So you took 80% of your data as training, and then you're going to test it with the last?
Yeah, I took 80% for training, 20% for testing. That's been recommended to me as a kind of best default practice, but yeah, your mileage may vary with different problems.
Feel free to just give a short answer if it's not that useful, but if for this really simple example, the default of the neural network wasn't enough, why would it be set so low?
Sorry, could you rephrase the question?
I guess if you consider that you're normally trying to use this for useful use cases where you can't just write a simple function, why would the neural network default be so low compared to therefore when you switch 1,000 because
I see. So why would scikit-learn default to doing 200 training iterations when I need 1,000 even for this really simple, silly example? It's good for experiments. You can see the output here. The loss number represents. That actually trained really poorly. I'm going to rerun this. This is legitimately a thing that can happen where it was randomly initialized and it picked an initialization which was really bad and it didn't ever land a good result. Yeah, you see that this training run has already gone better. Pro tip, if you get terrible results the first time, just try training again before you try changing your entire model. It's worth it. Yeah, so you can see this loss function going down. If we ran this for 200 iterations and we were seeing this loss dropping, we'd be like, cool, we're maybe onto something here. Let's run this longer and go make a cup of tea.
Explain how it knows, what's the definition of the loss? Like, how does it know what better is?
Yeah, so what's the definition of loss? How does it know what better is? I don't actually remember exactly how this loss number is arrived at, but it's to do with how many things it gets correct versus how many things it gets wrong. So for each one, it's trying to output a fizz and a buzz, true or false. The more of those are what we expected to see, the closer it is to 0. The more of those are not what we expected to see, the closer it is to infinity. And there are lots of different loss functions that can be used. One of them is when you're plotting things, you're thinking of things as like a plot. It's sort of distances between things is a good way to think about it. How are we doing here?
What is it actually doing now? Is it taking, because the data set knows the answers.
Yeah, so
it's not looking at the answers except for the training.
It's looking at the training example answers. So for each one of these iterations, like we just ran 487 iterations, for each one, it went through all 80,000 of our examples, ran them through the neural network, looked at what the answer the neural network got was, looked at the answer we expected that was in the data set, compared them, and used those to calculate the loss number. And then it goes backwards through the neural network and tweaks what each neuron in the network does in a way that will guarantee a slightly better answer, which is to do with gradient descent, and we don't have time to get into the details of that. But the algorithm's name is backpropagation if you want to read up on that. Okay, we have a trained classifier, and we're also running very short on time. So let's see if we can get this trained classifier to do something for us. So let's try and figure out how well our classifier has trained. Like, how accurate is this thing? So the first thing I want to do is look at what the classifier's predictions are for our test examples. So I can say classifier.predict for the test examples for the bit columns values. So these predictions, which we can take a look at, each one shows us what the classifier thinks the answer should be for the values in our test examples. So, for example, for the first one, it's saying 1, 0, that means fizz but not buzz. So it thinks the first number is a fizz. How can we tell how good these are? Well, there are lots of metrics we could use. We could look at how many it got right. We could look at how many it got wrong. I'm going to use a thing called a ROC curve, and I'll explain why once we have one on screen to look at, because I think that will make more sense. I've written a little class that we can use for this, so I just need to quickly allow us access to my class. I think it's going to be here. Okay, so our ROC is going to be a new instance of this class, and I can say roc.add curve. Each of these curves needs a label, so I'm going to have one curve for fizz and a separate one for buzz. It needs predictions, which in this case we want just the fizz predictions, so that's every row, just the first column, and it needs truth, which is going to be my test examples, the fizz column. Oops, no it doesn't. Truth was the wrong thing there. Sorry about that. It should have been called expected. So I'm going to now show my curve. So here it is. Let's just shrink this a little so we can see the whole thing. A receiver operating characteristic curve. What does this mean? So on the vertical axis here we have the true positive rate. Now, true positive means the number of things that we labeled as fizzes that were in fact fizzes. And then across the horizontal axis we have the false positive rate, which is the number of things that we labeled as fizzes but we shouldn't have done. They were errors, they were mistakes. Now the way that this curve is arrived at is that we start by saying the threshold for calling something a fizz is 0. So the output of our neural network is going to be a probability, and what we consider to be a fizz or a buzz is going to vary depending on where we choose to put the threshold for that probability. So we might choose to say, well, the threshold is at 0.5, so any probability of 0.5 or above is considered to be a fizz, and any probability less than 0.5 is considered to be not a fizz. In this case, we consider lots of different thresholds. So we start by saying, well, the threshold is 1. Right? The threshold is exactly at 1. So absolutely nothing is going to be considered to be a fizz, because it has to beat a probability of 1, and that's impossible. So we get this point here, where the false positive rate is 0. That's great. We didn't mislabel anything as a fizz. But the true positive rate is also 0, because we didn't correctly label anything as a fizz. At the other end of the scale, we say the threshold is 0. Absolutely anything goes. We'll just call every single thing a fizz. Now, in this case, the true positive rate looks great. The true positive rate is up at 1 because we got every single actual fizz correct. But the false positive rate is also at 1 because we got everything that wasn't a fizz wrong. The rest of the curve is drawn by moving the threshold around. So we start with the threshold at 0, we slide it to 1, and as we go through, we plot out this curve. Now, if this were perfect, if it were getting absolutely everything right and making 0 mistakes, the area under the curve would be 1. The area under the curve here is 0.74. Let's just quickly add our buzzes to this, because we really should be considering both of them. So that's going to be that and that. This is just saying every row, and this time the second column. And then I can show this again. Okay, so our buzzes did really incredibly well, but our fizzes less well. So now we know kind of roughly how this performed. Let's try it out in practice. Let's see if we can make a computer play fizzbuzz. So we'll take all of this code, come back down to the bottom here, drop it in here, and I'm going to rename this function to fizzbuzzml. The only thing I want to change here is how we arrive at our answer to fizz and buzz. And this is going to be classifier.predict using an array containing the bits of number. And it's going to be the first result from that prediction. So let's look at this and see how it performs. 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, fizz, buzz. We did it! If you were ever asked to implement fizzbuzz in a job interview again, I hope this is how you do it. But...
Did you change the function you called?
Oh, no, I didn't. Oh, you can't... Did we do it? No! Oh, well, what I was about to say... No, great catch. I didn't change the function I called. What I was about to say, though, was even though we didn't see any mistakes in the first 15, we did. This isn't perfect. It's based on predictions. So let's see if we can get a better feeling for how well this did over a larger number of examples. I'm going to look at a comparison of the two versions of fizzbuzz we've produced. So I want to make a pandas data frame, which is going to contain a number and our accurate fizzbuzz of the number and our machine learning fizzbuzz of the number. And we're going to do that for, say, the first 1,000 numbers. Oops. Let's do it like that. And I want to call these columns N, truth, and ML. So let's look at the head there. So mistakes show up like this one where the truth and ML columns disagree with each other. So we can actually produce a diff from this. And we can say our diff is going to be equal to the compare. Now, this is a very cool pandas feature where compare truth is not equal to compare ML. So I'm filtering the compare data frame based on when those two columns disagree with each other. So you can see it's disagreeing a lot on the fizzes, on the multiples of 3. We can look at what percentage it's getting right. 94% accurate, that seems pretty good. Now, we know the rules of fizzbuzz, we know how to write a fizzbuzz program properly, so 94% accurate seems kind of terrible in this case. But if we didn't know the rules of fizzbuzz, 94% might be totally acceptable. And in fact, if we as a group of people in this room now were to play fizzbuzz to 1,000, which I am going to make you do, no. I don't know if we'd get 94% accuracy. Like, even though we know the rules, we might still slip up. Any final questions?
What is it about Python that lends itself to being so appropriate for machine learning that other languages or like technology stacks aren't as?
Great question. So what is it about Python that makes it so well adapted for machine learning? It's the ecosystem. So Jupyter Notebook that I've been working in, pandas that I've been using to manipulate the data frames, SKlearn that I got the neural network libraries from. All of these are backed by NumPy, which is this excellent linear algebra library. That stuff all exists for Python. It doesn't exist for Ruby, for example. And there's so far we'd have to go to catch up that honestly Python's pretty great. We may as well just use Python. I mean, things like this diff production that I did up here, like I love how easy that is with pandas. I wouldn't want to sacrifice that kind of power.
So we've gotten to the end of this, we now have an output, which is a model. And if so, then how do we take that and put it into, say, a web app to actually?
Yeah. So is the thing that we have now a model? So this classifier object that we have contains the model for us. And really what the model is the structure of the neural network and the weights that have been applied to each of the neurons inside that network. We could serialize those weights. There are 32 inputs, 32 hidden layers, and 2 outputs. So that's 66 numbers. So we could output those 66 numbers and a bit of metadata about the type of network we have, and that's all we would need in production on our web application to reproduce this. So even with much more complex models and much larger data sets, even if you need to train on GPUs in some ridiculous server, actually deploying it, running it on a CPU in a normal web app is potentially fine.
But would you reuse those things? Would you rewrite them in Ruby, or would you have like a Python? Say we had a Rails app that accepted input. Like, what do we do with those?
Yeah.
With that model, those numbers?
So if we were deploying this to production, would we be able to use the weights and things in Ruby, or would we deploy a separate Python app? A concrete example of this is the recommended posts on the blog. Our blog software, Maitre D, is written in Ruby. Our blog recommendation system, which uses machine learning, is written in Python, is called Sommelier. And in that case, we just defined an HTTP interface between the two things, and that's how they communicate. It was easier to be able to use the library that generated the weights. I am aware of examples where people have done the experimentation stage in another language called R and then ported it to Python for production. So once they figured out what the weights were, but I don't know of a Python to Ruby example. We are 10 minutes over time, so I think we should wrap it up there, but I will happily talk about this endlessly with all of you. So find me, ask questions.